Welcome back, everyone. I'm Professor Rhett Smith from ProtonGuru.com. We're going to go over lesson 6.10 today, and we're going to address the nucleophilic acyl substitution reactions of carboxylic acids. Now, the carboxylic acid has an issue that other carbonyl species do not have. And to illustrate this problem for carboxylic acids, let's consider an amine as the nucleophile. Now, in our previous lesson, we saw that the amine was a great nucleophile to do nucleophilic acyl substitution on acid chlorides and in hydrides. But with the carboxylic acid, we actually have this acidic hydrogen here. And remember that an acid-base reaction is generally faster than a nucleophile attack reaction. So if our nucleophile is even a relatively weak base, we'll actually deprotonate the carboxylic acid to make the carboxylate. And in this case, the amine becomes an ammonium. So you make this ammonium carboxylate salt. Because of this type of reactivity, in order to get a carboxylic acid to react with an amine to do nucleophilic acyl substitution, you would actually have to first convert the carboxylic acid to a non-acidic group with a leaving group, like the acid chloride. Then you can react it with the same amine to get the amide, like we talked about in our last lesson. So this whole lesson, lesson 6.10, is about converting the carboxylic acid to the acid chloride, has a good leaving group, can do these really easy reactions to replace the chlorine good leaving group with a bunch of different nucleophiles like we saw before. So the goal is to replace an OH with a chlorine. Luckily, we've seen a couple routes to do that when we think about converting an alcohol to a chloride. So consider this case. This is not a carboxylic acid, this is just a regular alcohol. But with this reagent, thionyl chloride, we learned a mechanism in lesson 2.11 by which that OH group could be replaced with a chlorine group on the thionyl chloride so that our product would be this. We also learned that you could use phosphorus trichloride to accomplish the same transformation, again in that same lesson, lesson 2.11. Now I'm going to tell you that I can use either thionyl chloride or phosphorus trichloride to likewise replace the OH group on a carboxylic acid with a Cl group, just like we did to replace the OH group of alcohols with a chlorine. In fact, the mechanisms by which these transformations take place bear some similarities to what we saw with the alcohols. Perhaps not surprisingly, when you take thionyl chloride with this very, very polar positive charge on the sulfur, right? It's got the oxygen and these two chlorines yanking electrons away from the sulfur. So the sulfur has a lot of positive charge. It will certainly attract the lone pairs on that carbonyl oxygen. This leads to the compound in box A. This is very much like an attack on a carbonyl compound by a nucleophile to break a CO pi bond, but here it's an SO pi bond. And very much like what happens when you have a carbonyl with a minus on O, you're really trying to push that negative charge to somewhere where it would be more stable. Chlorine is a larger atom than oxygen, so pushing a Cl- off is favorable. And that leads to the species shown here. The unstable part of this molecule is there's a plus charge on the oxygen still, which makes it very favorable for the chlorine nucleophile to push its electron density at the carbon and up onto the oxygen. That will lead to the species where all the atoms are neutral, as shown in box B. Now, this group here happens to be a pretty good leaving group. So what we do is push these electrons up to this compound, and you have an SO2Cl, right, two O's and a Cl on the sulfur, leaving as an anion. Now, initially, that will lead to a protonated version of what we talked about as being our final product. Right, we have the chlorine on there still. The O has a positive charge because we've made a new bond to it. It already had the H. And the R double prime group is still attached with a single sigma bond. Now, just a simple deprotonation of this will lead to the compound shown here, where we now have the acid chloride, and the carboxylic acid that we started with in the net reaction has been converted to something with a good leaving group that's not susceptible to being deprotonated like the OH group in our initial species. Reaction of the carboxylic acid with the phosphorus trichloride follows a very similar pathway. You see a very partial positively charged phosphorus due to these electronegative chlorines being adjacent to it, so it attracts the lone pair from the carboxylic acid oxygen. the species in box A react with one another, right? We have this chlorine that came off as a chloride, and we have a positive charge on this oxygen. So nucleophilic attack leads to the species shown here. And you'll recognize this step as being very similar to what happened with the thionyl chloride reaction, where we'll make a new double bond between the O and the carbon, but that O with the double bond happens to have a hydrogen on it still, so we actually have a positive charge on the O until we do some other step to this. We have the chlorine, check, and the R double prime, check, and here's our leaving group. O minus, phosphorus with 2 chlorines on it. Now, the positive charge on oxygen is not very stable. The minus charge on this negatively charged O PCl2 species, not very stable. So deprotonation of that species leads to removal of this. Got 2 more chlorines that you could use to do this 2 more times. But the organic piece we get that was derived from the carboxylic acid now is this species. So we actually have the acid chloride as the net result of the reaction of the carboxylic acid with PCl3. This is a very common and useful strategy to take a carboxylic acid and make it into a species that can be very, very easily reacted by the nucleophilic acyl substitution with a variety of different nucleophiles, like we talked about in lesson 6.9 of the primer and our video lessons here.